we don't have that curve available, so we'll have to evaluate those two functions numerically as shown here. So here's our original desire to find this integral. And then we do evaluate at the right sample point here and at the left sample point here by putting the sample point value, in other words the abscissa, into the polynomial locations. Carry that out and you get 0.16666 and so on to as many figures as you'd like. The analytical answer can be done in the conventional way and evaluating the quartic function at the left and right ends, and you get 1/6. So you really have an exact answer to that problem. Now, there isn't any error in the algorithm involved here, but there could be round-off error, and I'd like to distinguish those two. Sometimes, and I've seen in textbooks where people have illustrated Gauss integration and have not pointed out the distinction because they've done sample problems that should have been exact, and they get error in something like the third or fourth significant figure, and it leaves the viewer thinking maybe it's approximate. So Gauss integration is either exact or it isn't for a given function that you're integrating. There are two modifications to Gauss integration that can be easily done. The first one would be to fix one of the sample points a priori at one end of the symmetric domain. The reason you might do this is that there might be some physical application where you already know something about that end, or there are some cases where that end is special. For instance, there is a case in the literature of a triangle in which there are lines upon which this integration is done, and they intersect at the left vertex, and so that point was chosen a priori. What that does is basically rob you of one of your defining equations, because the location of that sample point is not left to be part of the solution. In other words, it's not optimum. Lobatto is a similar idea, except that you would use both endpoints and thereby eliminating two defining equations. So there's a little loss of accuracy here, but perhaps some convenience in special applications. The work that we've done so far has been for the symmetric domain for ease of computation. But now let's try to connect back to the real world. Our original integral really was this integral on the domain AB, shown in this figure, and what we've done basically is convert that over to the symmetric domain. Now, how is that really done? Well, it's basically the change of variables in an integral. So there is a linear mapping, it turns out, that would let you go back and forth between the x and the c variables. That relation has a constant shift, which effectively shifts the center of the physical domain, and then it has a stretch or shrink factor to account for whether the physical domain is bigger or smaller than 2. And what our goal should be really is to convert one integral into the other and see how that works. So we'll take the physical integral here and turn it into a variable or an integral on the dc variable. To do that, you need to evaluate the integrand at the c location. That doesn't require anything particularly special other than the notation. But you've got to change the limits, and you've got to change the integrating variable. Now, the integrating variable is changed by taking dx equals 2, and then you merely do the differential form of the equation above to get that it's this stretching ratio times dc. This actually is sometimes called a Jacobian. It's a stretch ratio when you're going from one integral to the other. And then that will show up here where dx used to be. Then the upper limit that would be x equals b would be for c plus 1. You can show that by putting b into this formula and then calculating c. You might want to pause and do that just to prove it. And likewise, the lower limit goes with xi minus 1. So all told, we've now converted from the real domain over to this symmetric domain. So we will factor out the stretch constant from the integral, bringing it in front here. Interestingly then, this integral now becomes the symmetric form that we work so much with, and we'll replace it with our series of weights times sampled functions. Now, up to this point, we've sort of been talking about going from the physical world to the symmetric artificial world, but at the last step, as we see here, we can actually interpret this in the physical plane just by realizing that the xi can be mapped into the x, and if you allow me to call those the x sub I, which are the sample points in the real world, this formula now has been converted to one that can be used directly on the non-symmetric domain. Finding these x sub I is not hard because you use that linear mapping that we started with. And indeed, all these formulas let you go back and forth between the two domains because they are linearly related. Now let's move from one-dimensional discussions of Gauss integration over to two dimensions. Here, if we have an integral in 2 dimensions, we'd like to replace it with a similar series that we used before. It would be a finite series with n sample points. There would be weights times functions that are sampled at certain abscissa. But the location of the sample point this time has 2 coordinates. There would be, for such a sample point, both a xi sub I and an eta sub I measured from the origin. Each such term in this series then would have 3 coefficients to be discovered and would require 3 defining equations. Okay, so you can add up the number of sample points required to give certain accuracy in general polynomials. Now, let's take an example of the continued polynomial expansion below here, that 3 terms would be sufficient to have a complete linear polynomial, and that would take only 1 sample point. If you had a complete quadratic polynomial, you have to come out to, to d c squared, this one here. It would have 6 terms, and that would take 2 sample points. If you go to a complete cubic, out to this point, you're going to have 6 plus 4 is 10, and for that you're going to need 4 sample points. So this continues on, and I've summarized that in the next figure. In fact, I carry out this logic all the way to a quintic, where you have to have 7 abscissa. But you know, this really isn't done in practice by using consistent Gauss integration for the dimension involved. Instead, people actually use one-dimensional ideas repetitively. And in some ways that's a disappointment, but it shows how tough a problem it is. I think maybe in the future people will be developing true 3-dimensional Gauss integration more. What we're talking about is roughly along this idea, and this was illustrated by Zienkiewicz in his book, that if you have a function, and I'll take a specific function just to tie this down, that when you integrate in one direction, say across the xi, so you're taking a cut through here, then what you're doing is replacing the first integral, the xi integral, with this series of terms, and which requires evaluating the xi sub I at specific points. Then viewing that as an integrand for the second integration in the vertical direction, you're required to make the same kind of cuts on the j variable, so you have weights j and eta j terms. By factoring these out together, the weights out together, you get a combined weight times a function that's evaluated alternately at the ith points and the jth points and so on that are needed here. And these are the kind of ideas that are used in practice. This seemed like real magic to me, but I started following it in regard to certain simple functions, and it seems to have logic. But it's a complicated idea. I think that the development of Gauss integration in 2 and 3 dimensions has become more of a mathematician's area than an engineer. So I think we can relax and conclude that the codes are doing these ideas in correct ways. We need to tie down our theory a little bit and show where it's used in finite element applications. I stated this earlier, that our 2 big reasons for interest in Gauss integration are integrating the strain energy density that leads to the stiffness matrix, and then secondly, finding the equivalent nodal loads. Both of these would be very difficult analytically, especially on the more complicated elements. And so you'll find most of the advanced elements now are being numerically integrated, and most of those are done by Gauss integration. I'll sketch a few typical elements that have been numerically integrated. Here's a 4-noded rectangle with, as you would expect, a rectangular pattern of Gauss sample points. Here's a quadrilateral where the pattern now would have to be skewed to reflect their mapping from the C-eta coordinate system. That's not shown here, but would probably extend something like this, and we know that we can go back and forth between those coordinates. Merv Olsen, who was a Caltech classmate of mine years ago, did a clever triangular element in bending. He used one sample point at the left vertex, which was fixed a priori, and then allowed the other 2 Gauss points to slide along these dashed lines to find their optimum location. Lastly, here's a solid element with a 2x2x2 pattern shown. Irons figured out this numerical scheme some years ago. The MSC Nastran version is called the Hexa, and it actually uses a 3x3x3 pattern for the direct strains and a 2x2x2 pattern for the shear strains. And so you can see that people are starting to tinker with the Gauss points and how many to use. Also, some of the codes, particularly the nonlinear ones, will allow the user to choose how many Gauss points are needed through a given thickness. The first problem in our problem session will be an unsymmetric Gauss integration. We want to find the integrand, which is a quartic, integrated in the region from 2 to 10. We would be happy to have an approximate value of this integral, so we're specifying a 2-point Gauss integration. Does that in fact, however, give you an exact answer? So we're expected to do the integration and then comment on the accuracy. Our solution will not be exact, and the reason is that the function that we're going to evaluate is a quartic. That means it has 5 terms in its polynomial involving 5 coefficients. 2 sample points will only give 4 defining equations, so we fall short 1 polynomial degree. We could integrate a cubic exactly, but not a quartic. The unsymmetric formula here for this integration involves the stretching ratio, the weights, and then the function evaluated this time at the physical coordinates x1 and x2 that correspond to the one-dimensional Gauss points. The linear mapping involved has this shift. Now we'll look at our first Gauss point. It'll involve this shift, this stretch, and then we'll have to insert the first Gauss point in the C variables, which we do here, and we come up with the first physical integrating point located on the axis below. The second integrating point is found likewise. We had a negative Gauss point, and when you put that in, you find this location. So you can see that those are symmetrically displayed and between the interval 2 to 10. We can complete our solution now because we can evaluate that function at the sample points. We know the function analytically. We put in the value of the Gauss points to get the sample at x1, put in the Gauss point to get the sample at x2, and we get these two rather large numbers. When we add the stretching involved, we find that there's a weight of 4, and we end up with this minus 56,000 number. The analytical solution, on the other hand, is given below here and done in the conventional way, ending up with a fifth degree polynomial evaluated at the endpoints, and there you get a similar number, large negative number in the 57,000 range. And our Gauss integration was within 1%, but it's slightly low. Now that would be useful then for many purposes. Problem 2 requires the viewer to develop a special purpose Gauss integration formula. This is a little contrived because we're trying to think of an integration procedure where you have a formula that is a quintic polynomial at most, but has no linear or constant terms. And since you will be doing this same type of polynomial over and over, it's proposed that it's worth your while to develop a special formula that doesn't need to integrate constants and linear terms. You need to develop the defining equations and then solve for the abscissa and weights. Well, the solution first would involve determining how many sample points are needed, and since there are 4 terms in this family of polynomials, you're going to need 4 defining equations. That will require 2 sample points because each one gives 2 defining equations. The new Gauss integration formula is shown here, where the weights W1 and W2 are not the conventional ones, and neither are the sample points. Probably. We couldn't say. They may still be spaced somewhat close to the optimal one-dimensional case, but we don't know that yet. Okay, so we're going to start out with our first defining equation for a quadratic. This is the first polynomial term that can enter. And as we've seen before, and working on the 2 sides of the equation, the exact integral under the parabolic curve is 2/3, and then we evaluate the function picking up the c1 squared and the c2 squared. The cubic polynomial likewise is integrated, and the exact value is 0, and then we end up with the cubic terms. We continue on with the quartic and the quintic equations. I'll just write these down without drawing fancy pictures, and the quintic again is an odd function with a 0 value. So this gives us 4 equations in 4 unknowns. If we make the symmetry assumption, and this time I'm going to be pretty bold in order to crash through this quickly, I'm going to assume that on this symmetric domain, both the sample points are symmetric about the origin and the weights. We assumed the first and found the second as a consequence in an earlier solution for the classical formula, and now we're assuming both of those symmetry ideas. We'll use those symmetry assumptions now to simplify the 2 equations that we need. Equation 1 involves both weights and both abscissa, but we set W2 equal to W1 in this location, and then we set C2 equal to minus C1, and then when it's squared, it comes out positive. The right-hand side can be summed to give this expression, and then gathered over here at the right. It turns out we need to use equation 3, which was the quartic equation, and When we do the same process and then gather these terms, we end up with 2w1 c1 to the fourth gathered over here. Now these are two nonlinear equations in two unknowns, and in general there could be many solutions or no solutions. Nonlinear equations can be pretty difficult. We need solutions for the abscissa that lie within our range from -1 to 1, and that would certainly be one condition that we would put on. It turns out you can solve by dividing equation 3' by equation 1', and that will eliminate the weight, you see, and give you an expression only for C1. C1 then pops out directly and comes out to be this particular square root. C2 would be the negative of that. Now, knowing those numbers, you can go directly back into either equation and find the weights, and so we use equation 1' for the first weight, and then the second weight has been set equal by symmetry. So we do end up with an integrating formula. This is an exact formula for that class of functions that we wanted to attack. Problem 3 is more of a rote exercise where I'm expecting people to turn the crank and grind out a Gauss integration. We've been given a polynomial here which has 6th-degree terms. We're asked to do the symmetric integral over the region -1 to 1 using Gauss integration and 3 sample points. And then we're asked to comment on whether this is exact or not and why. Now, this is going to require looking up the weights and abscissa from a table, and I have some in my course notes, and any textbook on finite elements would have such a table. The formula that's used is this one with these weights, these 3 weights, and then these 3 abscissa, including the one at the origin. And notice the symmetry again. We have a point at the origin, and then we have plus and minus numbers symmetrically disposed about the origin. Now, will this give an exact integration of a 6th-degree polynomial, which in general could have 7 constants in it? And the answer would be no, not a conventional Gauss integration, because it would have had 6 defining equations and would have been optimized to integrate the constant, linear, and so on up through the x to the 5th terms. So you would need a 4-point integration to get an exact answer. The evaluation of the function at those 3 sample points is the biggest part of the labor here, and we'll just skim through that quickly. Here we actually take the known polynomial terms and put in the first sample point and evaluate it. We then take the second sample point at 0 and evaluate, and that number is an easy one. And then we do the third sample point. We put those 3 contributions into their respective locations here and sum it up and get this answer. If you do the analytical answer, it's slightly higher, so we've underestimated a bit here. 12.96 versus the exact answer 13.14, but pretty good. Problem 4 has to do with Gauss integration of a beam element, and I'm going to try to tie our theory a bit more closely to finite element theory now. Suppose that you wanted to use Gauss integration to integrate along the length of the beam, that's the x direction, in a 2-noded Euler-Bernoulli beam. Now that's the standard Euler-Bernoulli beam that we've studied earlier. How many Gauss points are needed for an exact solution for the stiffness? How many Gauss points would be needed for an exact equivalent nodal load set up to parabolic load distributions? Really interesting questions. Now, you can see in the solution that the key is going to be that the beam shape functions are cubics. So we'll exploit this cubic nature of the shape function a lot. First of all, the shape functions enter into the stiffness integral in this manner with two derivatives. Now, since nx itself is cubic, two derivatives would be linear, so the integrand here would be a quadratic function of x. Therefore, there will be three constants involved in that polynomial, and that will require two sample points to define to get an exact answer. Likewise, if we do the equivalent nodal loads and we have a cubic function here, and if the distributed loads are as much as quadratic, then you've got degree polynomials 3 here, 2 here. That means the integrand in total is quintic. In other words, 5th degree polynomial. Now that will have 6 constants involved and will require 6 defining equations, and that's supplied by 3 Gauss points. So interestingly, the stronger criterion is the one for finding equivalent nodal loads exactly. In problem 5, we're asked to develop a Lobatto integration scheme. Given that there's a series of cubic functions to be integrated on the symmetric domain from -1 to 1, we're asked to use Lobatto integration and find the abscissa and weights from first principles. And when we get done, we'll compare with Simpson's rule. At the outset, it doesn't seem there should be any connection because it's a completely different classical method. Okay, let's solve this. The cubic has 4 constants, therefore we know we need 4 defining equations. And here I've written down a general cubic showing those 4 constants. Now, the function is shown above, and in the Lobatto method, you a priori say that you're going to sample at the 2 endpoints. So that, in effect, uses up 2 defining equations we might have had. So our 2 sample points only yield 2 defining equations. So clearly we need a 3rd sample point. We can do that by taking a point somewhere in the interior, which we'll call C2. I'll write down our new Lobatto integration formula here. It has this series of 3 terms involving the red quantities that are unknown at present. We have the 3 unknown weights and then the 1 unknown abscissa. The defining equations are done in the same way as before, except that we know the location of the sample points at the 2 ends. We have to again integrate the constant, the linear, quadratic, and cubic terms, and we put in the values that are exact for those integrals. Then for the evaluation, we enter the sample point evaluation here in the middle term, and then we have the location of the sample points at the left and right end, and so we're able to enter those in those corresponding spots, and that gives us 4 equations and 4 unknowns. To solve those 4 equations and 4 unknowns, we'll take some treachery and cunning. One way is to recognize that symmetry again would require that the center sample point be at the origin. That knocks out the highest degree equation, namely the cubic one. And then we can write out the other equations, and those come in rather nicely when we put in the 0 for the central sample point. And if you take the second and third equations and add them directly, you get W3 is a third. That's a third weight. But then the second equation proves the symmetry of the weights. The first equation then will give us the remaining weight at 4/3. This leads to an integrating formula here And as we look at that, we see it's a third of the function at -1, 4/3 at the center, and 1/3 at the other end. And that's exactly the same as Simpson's rule. So in this case, the even spacing didn't seem to give us much additional accuracy over conventional methods.